the Center for Speech and Language and the Center for Imaging Science. Our speaker today is Dr. Yi Ma. He received his PhD in Electrical Engineering and Computer Science from the University of California at Berkeley in 1998. And then he was an assistant and then associate professor at electrical engineering at the University of Illinois. For the last 5 years, he's moved to Microsoft Research Asia, where he's the director of the Visual Computing group at Microsoft Research. Yi is one of the rising stars in the field of computer vision. He's had numerous influential works in the area of geometry originally, and more recently in the area of sparsity and optimization and sparse representation for face recognition. His paper on face recognition is one of the most cited papers on FAMI in the last 5 years. And we're really honored to have him, and welcome.
Thanks a lot. Thanks a lot for having me, and also very glad to be here and seeing his beautiful house and wife and kids. And it's always a pleasure to visit Baltimore. I always feel this is every time I visit here, it's very, very pleasant. And also that today, I mean, I'm just here to try to give a talk that I have given recently many times. That it's actually not a talk about one specific work. Piece of work is actually probably an ensemble of work that in one topic. So it's actually a collection of works from me, my students and colleagues, and also that even in some of the related area. So, but it's to me, it's a very, very interesting story. I mean, probably one of the most beautiful story I have seen in my life. That really, that we will see that it's really carry this very, very important message that when we truly do scientific work, how theory, algorithm, applications that be able to go hand in hand and be able to really support each other and improve each other. Right, so it's you will see that this lecture is trying to carry a little bit of that. So how important it is to really to do some fundamental research and how that be able to change the engineering practice, even you are in the industry, right? So this basically the work is trying to find a low-dimensional structure in high-dimensional data, right? So I don't have to overemphasize what's important about data these days, right? Everybody's talking about big data and high-dimensional data, right? The data we're dealing with, especially at industry, images, videos, user, consumer data, and all the internet web data, right? So of course, the data, we all believe that the reason we can do something interesting is that they have structures, right? They're not random. So the question is that who can get those structures well? And whoever can do a better job, you really be able to win in business, at least. Industry, that's what it is. And also that the data, the structure very often are highly low-dimensional compared to the original dimension of the data, right? For example, if you have an image, the resolution usually right now is 10 mega. Easily you get a picture. Even the cell phone takes 10 megabit, the pixel images. The question is whoever can get the information of the data, more importantly, that actually serves almost all the applications, right? That compression, transmission, and indexing, and also classification. Almost to everything. So that's what the question is, how do we do this, right? The data obviously has structure. So in this lecture, because I come from a computer vision background, an image processing background, so I will use primarily images to carry some of the abstract notion because they're very intuitive. But the method and the theory that you'll see in this talk applies to very, very general the signals and data, right? But you'll see primarily images in this talk. So for example, what we're talking about is that, let me grab a, right. Put my pointer. Anyway, it's okay. I'll use what's on the screen. I can use the screen. Sorry. This one probably works. Here. So, for example, if you look at the picture like this, right? So, if you think about it not as an image, but think of the image as a matrix, right? So, obviously, the matrix is not a random matrix, Right? So the columns are highly correlated. Right? Although maybe you're looking at a 100 by 100 pixel matrix, but the number of columns that are independent are probably just 10 or even less. Right? They can span, all the other columns can be written down as a linear combination of the rest. So that's it. That's what we mean by you have structures in the data. Right? So you don't need a 400 by 100 matrix to represent it. You only need maybe 5 bases or 10 bases to represent it. So then, of course, if you examine data like this, you can start to see that they're actually not a structure. They're actually structured across all scales. Right? Very semi-local, local, semi-local, semi-global, and global. So how do we describe the structure? How do we actually harness them while we're trying to do all kinds of signal recovery or recognition tasks? That's really the game here. Well, everybody sort of know, right? If I wanted to get a low-dimensional structure, one of the probably this is for most popular techniques is the PCA, right? So if I visualize this picture as a matrix, each pixel as just entry in the matrix, so those are just the columns of those matrices will be highly dependent. In order to find what the column spans, a low-dimensional subspace, I only have to just conduct a singular value decomposition and throw away the smaller ones, and you'll find the leading singular vectors. That will span the basis of this subspace. So this is a very typical procedure. Probably everybody in this room knows how to do it. I mean, my lab, this is one line of code, right? And of course, in practice, you not seeing the low-rank structure, low-rank matrix precisely. You see maybe a little bit contaminated, a little bit corrupted matrix by Gaussian noise, for example. Right. Turns out, again, singular value decomposition actually give you the statistically optimal estimate of the low-rank matrix if you follow the procedure. So this is all good. I mean, because this is probably the most popular, mostly used techniques, multivariate statistic techniques in human history. Right. So, well, since day one, actually this was invented about more than a century ago. And has been used extensively. But since everyone's invented, people know that actually PCA is very brittle, in the sense that it's very brittle to corruptions. What we mean by corruption, meaning that if you can take any pixel here, one entry, if you can arbitrarily corrupt, add a very large value to it, and if you follow the same procedure, the subspace you find then can be arbitrarily far from the ground truth. Right. So you can arbitrarily perturb the estimate by just corrupted data in a very, very few entries. Right. So that's very bad, at least for our applications, for computer vision. Why? Because this is the kind of data we deal with all the time. Right? So, I mean, this actually, in recent years, I came to a realization that it's, why we're suddenly, there's this reinvention or invention of all these new tools, new techniques, right? Why we cannot just follow exactly what all the theoretical framework that was established in control, in signal processing, in estimation theory, in optimization, and also in information theory before and be able to solve our problem? Well, because there actually has been a very fundamental change of the regime, especially engineering regime, right? Because the traditional theory of electrical engineering and computer science was established 50 or 60 years ago, where you very much have full control of the data acquisition process. You build the devices, you build a telescope, you build your circuitry to measure whatever you want, right? If something malfunctions, you throw it away, you build another one, right? But these days, as engineers, we very much have lost control of the data acquisition process. You solve problem based on data that is presented to you. Right? Nobody is going to give you another batch of data. For example, face recognition. That's a picture given to you. You cannot grab the girl and ask her to sit down and take off the glasses and take another picture. Right? And you can take this picture that maybe someone showed to you. Or you cannot go to the very side to take another picture. So the question is, how can you still recover, but there's still information in the data. The information we care is still embedded in there. The question is, how do you deal with this kind of situation? When the data is incomplete, when the data is distorted, when the data is corrupted, where all the conventional techniques obviously start to fall apart. Actually, the story is actually not new, right? Because there's a very interesting history, right? So I mean, every problem you see today is not new at all. Very since the day where estimation theory or signal processing was started, what became to attention to mathematicians and engineers. Right? So everybody is familiar with this picture, right? We solve least square. So basically your measurement is very over-complete, and X is what you're trying to estimate with some Gaussian noise. That's a geometry everybody is very familiar with. Gauss wrote probably one of the first paper, very, very influential. Why? Because why for 200-300 years, that is the most popular regime. Precisely what I said. You know, that if you control the data acquisition, you can wait until you have enough data, right? In order to predict the trajectory of the planet, you can wait for years. And you make sure, you know, someone wipe the lens very clean so that you don't get corruptions. But very interesting that there is a paper just exactly around the time of Gauss by Bartkovich. And I don't read French, but probably René did. And this is exactly about the suggestion using L1 minimization to solve linear equations. Actually, it's very much probably one of the first L1 combination. And Gauss actually was one of the reviewers of the paper. He actually made the comments. If you can go trace back the historical documents, he actually exactly suggested in doing this, we'll be able to help correct errors better than just do least square fitting. Right. Of course, the theory wasn't full-fledged and everything. I mean, the question is, I just wonder why that paper has never got much attention than the least square. Now, these days, everybody's doing this picture now, right? Because the engineering practice has changed. The problem, the nature of the problem has changed fundamentally. So very often you're dealing with incomplete data. You still have to solve for X. The data can be highly corrupted by Laplacian, by highly, distribution with very heavy tails and so on. Right? Again, because of engineering practice, because of availability of data and computers, computation resource, right, the problem actually become more urgent. Whoever, as I said, whoever can do a better job, you make good business, right? And also, there's actually a very interesting time of history because the theory, algorithm, and application has all gone through tremendous progress in the past few years. Right? There's a tremendous confluence among them. Right? Really drive this field at a very, very high pace. Even I'm in the middle of it, from time to time I really feel that I'm really catching up my breath very, very slowly, very, very, very hard. I'll just give you a little bit of contextual information, what's been going on. So, for example, everything sort of started from interested in solving this kind of problem. I have I try to solve a linear equation, given y and L, I'm trying to solve for x. Obviously, here, if L is the fat matrix, I don't have enough equations for the large number of variables here, x. But the only hope you have is that x has some structure. For example, x maybe is very sparse, has very few non-zero entries. Right. So at least the problem may have a solution, but finding the solution may be very difficult. People know this is a very, very highly combinatorial. The break people get is that it turns out that actually this causal problem under fairly broad condition, you can relax use and solve them very, very accurately and correctly using L1 minimization. Just relax the L0 norm with its 1 norm, which is a convex program, and it can be solved in polynomial time. Right? There's a full-fledged theory now, fully characterized exactly when and how you do this. And again, one of the first my encounter with L1 is that I just apply this to just face recognition, just see what happens at the time, even without fully understand what the heck we're doing, to be honest. So, for example, you can model the face recognition just as the query face as a linear combination of what's in your database, apply some corruption maybe. Right? This is probably a very naive, straightforward formulation of the problem. And so you end up solving this kind of equation, again, the linear program. Actually, that really got us surprised because it started to give us very, very incredible solution because, see, here we started trying to just correct some sparse errors. Turns out you get more than what you bargained for, right? So this is actually an input image with 30, 50, 70% of pixel arbitrarily corrupted. I think I gave a talk about this just probably a few years ago here. And this is just a little bit overview. And you can see up to 60 or 70% of random full corruption. The computer still sees who the person is, and you don't. And this is sort of a dense error correction phenomena we will see in high-dimensional statistics. We'll see another example on a matrix as well later. Obviously, I mean, this is all about the vectors, right? Those vectors, x and e, are sparse. What about a matrix? A matrix also has structures, right? So if I have a very low-rank matrix, if I hit it with some random measurements, can I recover it? So again, the problem is hard, but again, the convex optimization comes to rescue, and there's a full-fledged theory being developed around it. Has been very causing all kinds of excitement in all areas. Right? Then why should you care? Because these days almost the entire internet relies on all the money come from what? Advertisement. The advertisement comes from prediction. Right? You have to complete something you don't have. So for example, all the user preferences about products, everybody's doing shopping online now. Right? So how do you know I'm reminding the user something he might be interested? Right? You can only get that from people have similar taste with you. And that's in statistics we call correlations. Right? In algebra we call linear dependency. Right? So again, that's why this kind of class of problems pops up everywhere to help you process this high-dimensional data. Of course, the life is not even that easy. Sometimes the data may look like this. Right? They may have structure, but they're buried somewhere. Right? Not just one subspace. They may have multiple subspaces, and also contaminated. Well, I think Professor Levedel is the expert on this topic, right? He's doing some of the most exciting work in this area, and also Emmanuel Candes' latest work is also trying to provide very good theoretic guarantee for this class of problem, which in the past almost seems impossible, basically, to have scalable, guaranteed correct solutions. Right? A lot of techniques used to be very heuristic or very combinatorial or greedy. Right? But now you can develop rigorous mathematical theory and algorithm, guarantee correct solutions. Now in this talk, we'll just try to focus on one particular class of problem that I'm interested in recover low-rank matrix. Right? Something like this. But of course, life is not so easy. What you have is this. Some entries, which you don't know which one, are striked out, are corrupted. Even more difficult, you don't even get to see the full corrupted matrix. I may hide 30, 50% of the entries. Right? Can you still recover the matrix? Well, sometimes you're dealing with a more general linear operator. The measurement might be doing all kinds of entanglement of the linear measurements. Right? Can you still solve this class of inverse problem? You are only given D. That's it. And also maybe the projection Q, you try to recover A, E, and Z. Add it all together. Right? E will be the corruption, Z will be the noise. So of course this problem pops up everywhere. There are many kind of solutions has been given, proposed, derived, rederived, reproposed, right? So applied to different type of applications. So but here the question is, can we do something better? Right? Revise the situation a little bit. Can we really provide derived provably correct and attractable solutions? Meaning that I know exactly where the method works when the method fails. And it's tractable, meaning that it's scalable. Right? It's not a combinatorial, not NP hard. And also, can we derive provably optimal algorithm? What I mean by that is that you cannot improve the speed of algorithm, at least not qualitatively. Guarantee success and guarantee efficiency. Right? Now, once you equipped with such a theory and algorithm, we'll see what interesting thing you can do with the application. Or what kind of interesting problem the application will inject back to the theory and algorithm. Right? I think that's a very healthy, relationship. So as I said, we're not the first person to come to even think about the problem. The problem is very important itself. Right? This is a huge history. You can see that it traces all the way back. I only listed a few that I'm relatively young, I hope. So those are the few in my age that only in computer vision that I'm aware of, some of the key papers trying to address this problem. Right? If you go to any other literature, any other field, you probably can have hundreds of papers solving this exactly same problem. Try to make PCA robust, basically. Right. So one thing that probably some of you are already aware that I also gave a talk earlier about here, when you're facing this kind of highly combinatorial problem like zero minimizing, sparse recovery, and low rank minimization, you cannot solve them directly. You have to look at the relaxations. So convexification is one way to relax this problem. So instead of solving L0, you try to find the absolute value of the entries. That's a one norm. And also for the rank of the matrix, you can use the nuclear norm. Right. Again, it's a convex surrogate for the rank function. Right. So this picture carries that. So instead of minimizing this function, which is horrendous to do, at place doesn't even have derivatives, or the gradient doesn't suggest any direction for it to descend, you replace that with this kind of function. Right. So at least for this problem, you can prove if you do that relaxation, that brings you from an intractable problem to a tractable problem. You can hope to have polynomial time algorithm to solve these kinds of problems. But of course, everybody can do this as a heuristic. But the million-dollar question is, when the solution to this problem the same as the problem to that, the solution to that problem, right? When those two formulations are equivalent. So put your engineer hat, right? So then before you can prove anything, you try to prove something with MATLAB. Right? So we can do simulation. We just see how this works. Right? So this plot is showing that this is a fraction of the matrix. The rank of the matrix as a fraction of the dimension. This is a fraction of entries gets corrupted. So all the way up to 100%. This should be all the way up to 1. Right? As you can see here, at every point here is a setting, is how much rank, how much corruption. And at that instance, we choose many random instances. Just solve the convex organization. Since this simulation, we know what ground truths are. We compare with the ground truths and just try to see if we succeed or not. Right? The white region means that the color is white, means that you succeed 100% times. Every instance is correctly solved. The black, almost all instances are wrong. Right? And you can start to see this very interesting phase transition. Right? Below this curve, the convex organization solved the problem perfectly. Above that curve, nobody cares. Right? We cannot do anything. So, at least it works. The verse is very exciting because this is almost the region that you care in practice. So your data do have good structure. The contamination is not too much. Right? You have hope to hope for a good solution. Right. Of course, if you know where the corruption or where the missing entries are, the curve gets bumped up, but the qualitative is still the same. Right. Now the question is, can we do something? Explain why this works. Right. This is one of the first results we did with Emmanuel Candes. That turns out, indeed, you can actually characterize this behavior. Right. So as long as the matrix you try to recover, the rank is bounded from above. The rank can grow almost proportional to the dimension. You only lose a log factor. And as long as the corruption is up to a constant fraction of the entries, we'll see how far we can go with that fraction just in a second. Right? So solve this fixed convex optimization, give you the correct solution. Right? Just keep in mind that one thing actually I'm very kind of proud of that come out of the mathematical analysis is that you can always do heuristics, right? You can always suggest this, but you won't necessarily know what the lambda to put there. Then what you do, you can do cross-validation. You can try to set empirically, ask your students to try, right? No, it turns out, there's a very rigorous choice for it, right? You only choose that fixed number, you're done. There's nothing for you to tune. It's a convex optimization. There's the only unique minimum as long as the problem is well conditioned, and that gives you the correct solution. Right. It's a very powerful message at the time. Of course, after that, we try to do some, there's also extensions. For example, as I said, I can hide 90% of the entries. I only show you 10% of the entries. But this fraction is arbitrary. Actually, it can be arbitrarily small fraction. Basically, I give you a cooperative matrix. I only show you 10% or 5%. I ask you to recover the entire matrix. As long as the dimension is high enough, the problem is still well conditioned, and you can do a perfect recovery, just using the simple convex optimization. So that's the message. What about corruption? As I said, the corruption is harder, right? Because when you have corruption, you don't know which entries are corrupted, which entries are missing. So actually, there's something surprise too. Right? So the fraction of, under very much the same setting, the fraction of entry that you can crop arbitrarily, that the convex optimization still works, is a asymptotic approach to 100%. Meaning that if you have a very large matrix, if you know the ground truth is very low rank, you can crop the 95, 98, 99% of entries arbitrarily, and the computer doesn't know which one, and still get the ground truth. And we'll see actually a real example later on. This is not just that you can prove mathematically. This is actually something actually real, actually really happens. And of course, if you have a noise, dense noise, you cannot hope to get an exact solution, but you can hope to get a stable solution. And there's all kinds of theory being developed around how to do this better and better, get it much sharper. This works from multivariate, give a very, very sharp bound of the C. You can optimal bound on the C and so on. And also that this recent work that sometimes if you want to solve a more general problem, if I have a crafty matrix, I really want to project it onto the lowest possible dimension. Let's say still I can recover it. What's the lowest possible dimension I can do? And this is kind of a information theoretical lower bound, which is exactly the degree of freedom of your data. That is sort of the minimum measurements you need to even for the problem to have a unique solution. And you just have to have measurements just with a factor more measurements, then the convex optimization works. It's very, very sharp, so it's sort of in this flavor of compressors and flavor. There's actually, of course, there's another model. If you don't consider random corruption, you can consider deterministic corruption. Of course, the condition become much harsher for you to be able to do recovery. But the complement to the model we're considering here Z is the E is random. The MIT folks, the Shankar's work is all about deterministic recovery. Sort of try to worry about the worst case. So this is the landscape, right? So in the past 4 or 5 years, you ask some of the very theoretical people applied mathematics are busy for. They are very much busy for this problem. Try to understand, basically try to get to this curve. First to prove if such a curve exists and where that curve is. Right? There's a series of great work be developed. And from what I can tell you now is that, yes, this landscape, this phase transition landscape has been precisely understood. So you can prove rigorously that under this curve, convex optimization always succeed with probability 1. And above that, fail with overwhelming probability. Question?
So one would expect the matrix completion problem to be easier because you know where the entries are missing. But the bound on the rank is of the same order. Nonetheless, in the experiments...
that's just for this point. But I'm talking about these two regions are... So they all have the same qualitative behavior now. Just that this curve is much higher than that one. They all bends up all the way to 1. But this is much higher than that. Maybe I should exaggerate that difference a little more.
Where in the theorem do I see that the curve for matrix completion is to the top right of the curve for matrix?
Not in this talk. So that's actually recent work from Joe Traub and a whole bunch of works from a few other people to characterize this phase transition sharp. So the similar picture people already know, very precise, as I mentioned earlier, by Donahoe and Tanner on the L1 minimization. This kind of phase transition has been precisely characterized with high-dimensional geometry. And the same thing, the same story goes for the low rank now. So it's very, very pretty, very, very complete.
I just want to make sure I understand the assumptions in the theorems. Could you go back for a sec to theorems 3 and 4?
Oh, actually, I didn't elaborate on the condition precisely.
Yeah, so when you say random signs in Bernoulli support, do you mean that the sign of the next one?
Yeah.
Well, okay. I was thinking in theorem 3 you talk about random signs.
Yes.
Does that mean that the sign is chosen independently both of the position and of the position in the matrix and the magnitude of the error?
Yes. Yes, exactly. So that's actually for this to approach to 100%, the sign has to be random. That's the one tiny extra condition. So basically, it's even. You flip coin. Basically, you choose a magnitude randomly. I mean, actually, there's no probabilistic model. The magnitude doesn't have any model, right? It can be anything. Just choose a support as a Bernoulli distribution, and then you flip a coin. Right.
So this might be a problem for some practical uses where positive and negative errors don't balance
Yes.
or don't come from the same distribution.
So actually, the randomness is just a thing to make the proof more technical, more easier. But turns out there's a procedure you can do de-randomize. Of course, some of the conditions become harsher, So you lose some of that, but still the qualitative behavior is still the same. You may not get all the way to 100% and so on. Maybe cut by half, but still you get the same behavior. So again, the randomness. Yeah.
And on the matrix completion theorems, what are your assumptions about missingness? Is this missing at random? Or?
Yes, missing at random. Oh, there's actually, well, only in this talk is the missing support is random. There's a whole spectrum of work, right? People making assumption about distribution of the, the column-wise, all kinds of spatial structural sparsity, you name it. I mean, that all kinds of. I'll if I have time, I'll allude to that a little bit. What people are doing with extending this kind of structures.
So I think there's two orthogonal questions there. One is whether the instead of having independent Bernoullis, if they're correlated, so there's some structured sparsity pattern.
Yep.
But the other question is whether something is missing is correlated with its value at all.
Here, the value has really no model. The value is really the support of the missing entry and the corruption. That matters. Right? So actually, you can prove even for a one minimization, you can say the magnitude doesn't really matter. It's really the support of the missing entries, the sparse vectors. So yeah, we can talk about that a little bit later. Yeah. So anyway, the theory is exciting. Really tells us, this is a family of a problem that previously deemed as intractable. Right? So they said, well, no, it's not. It's actually tractable. You can solve, at least there's a hope to solve them in a tractable way. So you only have to solve convex optimizations. But after a while, you start to realize that the convex optimization itself is not a picnic at all. Right? It's not something you can, it's a lot of walk in the park. So it's a sort of a nightmare for optimization. If you present this problem to any, conventional optimization people, they'll say this is very, very difficult to solve. Why? The dimension is very, very high. As for many of the applications you see, the matrix you are dealing with is usually in the range of 1,000 by 1,000. Even for 1,000 by 1,000, that's 2 million unknowns, right? Both A and E has 2 million unknown entries. So you are trying to solve a convex optimization problem with 2 million unknowns. Right? And also, not only that, the object function you're dealing with is very elastic. It's non-smooth. Some cases you cannot even take derivatives. Then, of course, you can say, I'm doing subgradient descent, and then you suffer from 1 over k square root convergence. You have to wait forever to converge, and so on and so forth. And so basically, the quality of the function tells you how fast the algorithm can converge. Right? Let alone the scale of the problem, basically throw away all the second-order algorithm out of the window. Right? You cannot just forget about them, right? You cannot computations. You cannot even store them. You cannot afford the computational complexity for the scale of the problem you're dealing with. So that's why I pushed the entire optimization community back to first-order method, right? In the past 5 or so years. So, but there's some good news. I'm not interested in the entire problem, the causal problem, non-smooth problem, but for this problem, it has some good structures. For example, if I fix E, minimizing A has a sort of almost closed-form solution. Vice versa. So maybe you can design an algorithm based around this kind of special good structures about your problem, and that's exactly what happened, right? In the past few years, people utilize a different, better and better gradient descent algorithm, the proximal gradient descent and the accelerated proximal gradient descent. Then introduce a Lagrange multiplier because you have constraints here. Actually, many of those constraints. You have millions of constraints, right? So you really have to use so it turns out augmented Lagrange multiplier is a very, very effective way of doing it. And then to split the optimization in 2 steps using the separable structures, you can use ADMM. So that really has changed the landscape of optimization dramatically, at least for this class of problems. For example, for this problem, right, in the end, you end up with this very simple 3-step iteration. And everybody in this room can probably implement it in 5 minutes in MATLAB. And you get a provably converged, efficient, robust PCA algorithm, right? So the improvement is dramatic, actually. They all belong to gradient descent algorithm. But you can see that just be a little bit clever. What you do with gradient descent can make your whole life completely different. Like 4 or 5 degrees of magnitude. This is what actually results 10 years ago. On a typical computer like this, you can just solve RPCA in 10 seconds. I just come back from visited John Wright. He claimed he's doing all this video. You'll see some of examples later. Large video stream, RPCA, thousands by millions by millions in real time now. So let's just tell you how fast things are moving. Right? Well, turns out there's some actually great news, right? So it actually made even optimization people think twice. Some of the practice design of the faster algorithm start to realize that, well, this class of problem is not supposed to converge this fast, right? But why? Or even ADMM, right? Here we're dealing with 2 terms, but in practice people are applying to, doesn't matter, 3 terms, 4 terms, 5 terms, and so on. We just do this. It works. Why? So it turns out, it actually allows even the optimization field has solved, to me, what I know are 2 open problems. The convergence of ADMM for more than 3 terms, which was completely open till probably this couple of years. And also, the convergence of this class of functions, which is called the restricted strong convexity. It turns out in this class of function, they have some very, very nice property. That if you do clever gradient descent and projection, you should expect a linear convergence rate. Meaning the arrow drops exponentially. That's actually explain what this algorithm does, right? You don't need to take 20 steps. You're done. Converge to the numerical precision. Right. So, okay, I'm sort of halfway, but to just an overview of what the theory is really about, right? Keep in mind that we have taken 2 steps, big steps. One is that we're starting from a class of very high dimensional combinatorial problem, trying to solve sparse or low rank signals. From previously we thought was computationally intractable, to prove that very precise condition that under fairly broad conditions that this problem become tractable and it can be solved with convex optimization, and then also develop a very, very efficient optimization algorithm, basically from theoretical, from intractable to tractable to practical. Right? So once we have practical algorithms, then let's put back our engineer hats and see have some fun with it, right? So that's really the. So now, there's a homework, right? So if you tell your student, I have a tool, I can solve this problem now, go find me examples. Right? Just giving them the MATLAB code, go apply to some data, say, have some fun. So what kind of data you can come up with to that this will work? Well, I'm from computer vision, right? Some of the first example that we saw in the vision book is that how wonderful human visions are. We can complete textures, for example. If you look at a texture like this, we can recover what's going on behind. Right, now computer can do this too, and probably even better than human, right? Because this is what's inputted to the computer, and this is what's recovered. Right? And this is actually about 95% of pixels arbitrarily corrupted, and the computer doesn't know what it's looking at, and doesn't know which entries are corrupted at all. Right? Here you get the solution by solving a convex optimization which has no parameter. Right? So basically the information is in the data. Right, just for you to find correctly. Of course, you can make it more real. You can say that's a little bit cartoonish. Now we're going to see more and more real problems now, right, throughout the rest of the talk. Right, I can do this. This is a comparison with Photoshop. Right, in the Photoshop you have to carve out what you don't like carefully. Right, but still that it doesn't do a very good job. It doesn't, those floors are not even. This uses all this local patch. I don't know if you know this nearest neighbor synthesis techniques. Right.
Although if you look at the one on the left, it's actually regularized some of the windows, I think.
Yeah, that's what it does.
Which might be good or bad.
Yeah, so it's up to you. It's a personal taste. So, also here is that these are the things like this, but also keep in mind, this is all the computer knows. It doesn't even know which part you don't like. You do what decide for yourself. What he likes, because he likes low rank texture. He likes sparse errors, right? So we put the flavor into the computer. So this is also that it just shows you, once you have this perspective distortion, then the traditional method really breaks down, right? Because it really doesn't know what it's doing. It's just doing all those local stitches, right? And it completely screwed up here, the geometry. And also you can take out even bigger regions and take out the flag or the buildings. Well, actually, our initial interest in the kind of robust PC is trying to process face data, because I was for a long time interested in face recognition. Right. So I take what I said earlier back a little bit Because I said that when you have a controlled you can control the data acquisition process, you don't get errors. That's not entirely true, right? So for the face recognition, even you control the process very, very carefully, you still get errors, right? There's cast shadows, there's specularity, there's saturation in your sensors, so on and so forth. And you just don't get clean data. But this is what you do, is that you take a picture of the person under very different lighting conditions. All you have to do, just stack them in 2 columns of the matrix and run the algorithm. And this is what come out as a low rank, this is what come out of the sparse. By the way, so I want to make a point with my presentation. So in all the examples you see today, we don't do any image processing, we don't do any filtering, we don't do any feature extraction. Nothing. No edge detection, no corner, nothing. No hog, no dog, nothing. Right? No sift. And so basically the information, the point here is the information is already there. You just have to apply the right tool to discover what you want. Of course, it doesn't solve all your problems, but this family of problems, this does provide a very, very relevant and effective tools.
So in this case, you didn't have to align the faces?
So this case, yeah, this is aligned, but I'm just saying that you're not doing the... Well, we'll talk about alignment just in a second. Yeah, you're jumping. Yeah. Well, we'll talk about that just in a second. Yeah. In fact, some of the best detector and alignment now is done by these techniques now. You will see very new papers to come out. Right. And also, this is just to tell you how, because people traditionally using the lighting directions to capture 3D. In fact, the Kinect camera you buy from Microsoft using very much the same principle, right? You shed lights into the scene and you capture 3D. Right? Depends on the deformation of the lighting and deformation of this to capture 3D. So this is what people in the past be able to do with robust least square techniques. You get about 1 degree of error everywhere, average, and then the maximum is about 8. But the people in the past they thought this is already good enough, right? But now using the new techniques, you improve the accuracy by 2 magnitude, right? Because the information is already in the data. You just haven't extracted good enough. Of course, this is one of the popular examples. Now you can see YouTube. There's a lot of using this RPC to do the video foreground, background extraction. This is what I was telling you. This is a surveillance camera video. You don't do anything. Of course, it's static. We'll talk about alignment in just in a second. So this is just to stack the raw pixel of the frames into the matrix. That's it. Then you just run the algorithm, send it to the algorithm, you get the low rank and sparse part. And I was just saying that this can be, see, if you have 100 by 100 pixel, that's already 10,000 dimension, plus maybe 1,000 frames. Actually, now there are techniques to solve this exactly in real time. You can put a webcam anywhere. You can get a foreground background in real time using these techniques. So what other places, you can ask your student, what other places they get to see a partial low rank matrix, right? With highly corrupted and also very disguised data. Turns out we're also doing that all the time, right, in engineering. The panorama, right? This is the Google Street View data. Well, I cannot show the Microsoft data because of confidentiality, but anyway. But we're doing it, so that's what I can tell you. So basically, you can see this is the point, that you want to stitch all the data together, right? So that's exactly what's the case. But your field of view is moving, shifting. So you don't get to see a small window of the data, but you want to put them together. Of course, there's also corruption, the reflection, there's the cars, pedestrians. You want to remove them, right? So this technique also gives you a solution to that. So as you can see, it removes all the inconsistency very cleanly. This is compared with auto stitch and Photoshop. This is auto stitch using SIP feature matching. Question?
Perhaps this is a concrete example where the missing data is not uniformly at random, but very structured in a band.
Yeah.
So why does this work in this way?
I don't know. So actually about the structured signal is still how to even model them correctly. There are techniques we model them as a random field. It works better, but then we don't have a theory. We cannot prove when it works, why it works better. There are also other structural sparsity can encourage spatial continuity that prove what it works better. But what we found in practice, the improvement is small. So we might as well just run the basic one. It already works very, very well. So they remove the person, remove the car very well. Right? So actually life is hard, right? Sometimes you don't even get to see this. You see a distorted, highly distorted version. As I said, you mentioned that if your data is not aligned, then what do you do, right? You have to do something in order to see the structure, right? So for example, as a human, we're doing this all the time. If I show you a picture like that, right? I always hate this. Yeah, so switching from laser to this is not easy. So basically that if your human eyes are very good at it, if I show you a texture like that, picture like that, you know this is some texture rotated and with some scratch on top of it, right? You are doing that deciphering very, very quickly. But it wasn't very easy for computer, to be honest, right? Because now, if you look at the problem, if I am able to apply a domain transformation to the image, if I can rotate, let's say I find whatever domain transformation I can apply, at least there exists a transformation such that the structure will pop up. The data will become very low rank, very compatible, very compact, right? So can I solve this problem? Then I go back to my original problem. Yes, I'm trying to look for low rank plus sparse, but subject to a deformed data. Of course, now the tau is unknown as well. So even the object function here is convex, the whole problem is no longer a convex program because this introduced nonlinearity in your problem. Well, we're engineers, right? So whenever we see a nonlinear problem, what do? We linearize, right? So if you don't even know how to solve the linearizing problem, then you forget about the problem, pretend they move on. Right? So this is actually then what you do. You just linearize against the tau, and you just do this incrementally, right? Every time I just correct a little bit, push the data in the direction that the rank will be lower, the error will be sparser. That's it. That's all you do. So you just need to repeat until you converge to a good solution. Actually, that video shows exactly the convergence path for that figure. So I can show you more. So this the window. What you saw is the initial window. That's all you have to do. Put a window on top, and it will slap onto the shape of the data with pixel-wise accuracy. Again, of course, with this image, you can say I can do some edge detection, I can do vanishing points, I can do clustering, I can probably correct the distortion up to a few degrees of errors, right? That's what you do in the past. Here, you throw red window on it, you're done. It will automatically find the geometry. So in the computer vision textbooks, we're always giving examples that human can tell shape from texture. Well, this is really shape from texture you're seeing in action. Right? And this is actually give you a pixel-wise accuracy of the shape. I mean by that, because you can have a more arbitrary shapes like that. So what's changed? Nothing has changed, except just the distortion becomes a little bit more parameters, right? Rather than just homography, here you just a few more parameters to specify the camera position, few parameters specify the camera calibration, and maybe a couple of coefficients describe the shape in terms of polynomial. That's it, right? So, I mean, even the equation doesn't even change. D composed with tau equal to A plus E. Now, why you should expect to solve this problem very efficiently, even with more parameters now? Well, keep in mind, what's your measurement? If you have a 100 by 100 patch, you have 10,000 measurements. 10,000 measurements to help you to estimate 20 unknowns, that's really nothing. It probably is very, very well conditioned. But what do people do in the past? You extract some edges and features. You'll be lucky to get 10 or 20 features out of that. And you try to use features to put back those 20 numbers. Then that is very, very ill conditioned. Right? So we are actually infer those shapes and parameters in our head in a holistic fashion. We're using all the data, the shape of the data to do that. And this actually offers a tool like that. And also, the result is much, much, much more accurate. Right? So this video shows, just what that process is. Usually, if you're interested in the shape of that thing, just throw a window on top of it, and you'll slap on it. And of course, if you go back to the matrix coordinates, just see what the computer sees in terms of matrix. In the beginning, it sees this matrix. It doesn't like it because it's not low rank. So it will start to push it. So it just only push the raw pixel around, right? There's nothing. The only process is just interpretation. We don't do any other filtering. Right? And as a result, you get almost everything from the single picture. You actually get a shape, precise shape, and you get the camera position, the precise camera position, up to pixel-wise accuracy. And you can do panorama, you can do all kinds of interesting things now. Because why you want to care about the pixel-wise accuracy? Because, well, you can fool human eyes, right? You can do this thing, you cannot tell. And they say, this is also, if you go back to say what kind of other problem we do, Microsoft, we sells a lot of cheap cameras. Well, one thing comes with the cheap camera is that you have to do calibration, especially if you want to do something in 3D, which is exactly what Kinect does, right? So the calibration rig at Microsoft for Kinect costs a couple $1 million. They don't even do a very good job. So how many students has played with calibrations? Camera calibrations? Nobody? All the robotics people should do, right? So I was a robotics student. I'm the one, oh my God, give you all kinds of headache. Right, so what do you do if your advisor asks you to calibrate the camera, or you go to the internet, download the Caltech calibration toolbox, and take some pictures, and make some rig, take some pictures, start clicking on the corners, right? That's very much you do. So here you just take a picture and do a simple initialization. Because the calibration is really nothing but align what's supposed to be aligned, right? Just rectify things, find all the deformation and alignment. So you just several seconds. As I said, right now probably even taking less than a fraction of seconds to do this now. This was at least 2 years ago. So also for a single picture, human eyes, we see the geometry perfectly, right? We don't have to guess what the geometry is. You don't even have to label. You learn from examples. It's already in the picture. Right? And for doing that, you get a precise pop-up of the geometry, and including where you're looking at this picture. And you don't need to do anything else. Right. Question?
Yeah, so in this case, do you have a lot more parameters for tau? Because you need to find a bunch of different regions corresponding to polygons.
It's all just, you just have to prioritize what you are trying to get.
Right, so there's more than 20 parameters in this case.
No, this is just two homomorphy. Yeah, it's probably 10, 20 parameters.
So it depends on how many different planes you expect.
Yes, exactly. You will need a little bit of assembly. And we'll say more complicated. Of course, when the structure you're trying to recover more complicated, you will need a more complicated description. Question?
So I got how from a single plane you can warp it, but how do you do here to get the geometry when you have two planes?
Well, you fold. That's the point. You find where it folds well. So if you find the wrong places, only one places, the folding give you the lowest possible rank. The appearance the facade become correlated. Right. Of course, this kind of idea you can generalize to other things too. So this is actually an example we did. We call it, as I said. So this is just we take 8 pictures of around this octagon building at I don't know how many sites. So that at Illinois, as you can see that actually we tried. I've done structure from motion all my life. We tried all public or privately available pipelines for structure from motion to get 3D on this sequence. They failed miserably. You can probably guess why, right? Because there's all the windows are similar to each other. There's also reflection. There's trees in front. And this result is obtained in purely used regions. There's no features matching whatsoever. So, of course, I worked for Microsoft. You have to do something to pay the bill. So that this is one bit I did. So you can put on the, website. It looks very, very cool. Yeah, all the management are happy. Finally. So what about, so far you see examples of the information or structure encoded in a single picture, right? There's already a lot. What about multiple pictures? You should expect more. There's more redundancy, more structure in the data. Right? For example, what if there are a lot aligned? Of course, you want a procedure to align the picture and also get rid of the occlusions, right? It turns out that the problem doesn't even change from a single view. Right? Just all you have to do change is probably the class of transformation. You just need a few more parameters. But keep in mind, you also have more data now, way more data. So again, conceptually, the algorithm doesn't even change. You can very much use the same code cycle for this problem. Well, again, this is something else I did to pay the bill, literally to the bill. So this is it's actually, to be honest, the internet is like a dream for a statistician, right? This is all the data there. There's got to be something in common, the structure there. But how do you find it? What's to grab there, right? All the information and the faces. As I said, even you do a face detection, still the faces are not very well aligned. Maybe he doesn't like certain picture of his he wants to get rid of. right? He never have that hairstyle, right? I mean, that's actually come from the Time magazine logo, right? So you can do alignment using the techniques, align them better. So as you can see, the average becomes sharper. Even he's still not happy. You can see, just show him the low rank part, right? All the picture that he's yelling or his bad hairstyle are gone, right? This is all done automatically, and because all the inconsistency, the ugly part went to the sparse part, right? All the statistically inconsistent parts get in there. Again, if you have a video sequence, if it's not a static video, or especially someone shaking, this is actually a YouTube clip from Al Gore being interviewed, someone amateur shot it. Well, you can see that, here you can see that not only you align the stabilize the video, and the low rank part actually almost has higher resolution than the original one. Because it gets rid of all the block effects from JPEG and MPEG. And it almost looks like the resolution is higher. Actually, it has the same resolution. And you can do handwritten digits. You don't have to, I don't have to over. And it doesn't have to be a man-made object. In fact, all the object that has some structure in it actually works. Text, another man-made. Actually, text has a structure across all scale, right? Stroke, the character, words, paragraphs. Right? You don't have to recognize from this angle. So actually, there's a lot of Chinese in here. I'm very proud to announce almost all Chinese characters are low-rank textures, or robust low-rank textures. Right? Meaning that they're not low rank per se, but after you take out some very bad, weird stuff, it becomes low rank. And they self-position themselves, meaning that you can look at the character from any angle, they should correct themselves. I mean, even characters that you don't expect to have a low rank. I'm not talking about just horizontal vertical strokes. I'm talking about very general characters. For some reason, I don't know. In fact, it's for all fonts, all the popular fonts. Chinese character. All has the same structure, and we don't know why. And of course, then you can do, once you have a cell phone, you take a picture, right? You can recognize character. You don't have to risk your life to get into the traffic to take a frontal picture, right? And you're not that tall either, right? So, I mean, anyway, this just makes things much easier. And as I said, I mean, that if you're really dealing with imagery data, single image, multiple image, right? So there's a tremendous structure that gets extracted from the image data. And that, also all this theory really starts to unleash all the information, allows you to compute those information in a very tractable and efficient way, right? I'll give you a very, very quick example. Just open your eyes a little bit. Those are so far mostly my example. Some of the work done by my students and close colleagues. Those are the work examples throughout everywhere. I mean, I only highlight a few. 3D data, tons of structures, right? Whenever you see a matrix, think about this structure, right? Images versus words, right? Of course, there's some contamination in your data set. This helps you to clean. Document, right? You know all this Google about this PCA model. What about a better model, right? You don't throw it. There's a lot of noise. Actually, rank is about topic, background. Sparse maybe it's about maybe it's about keywords. And this is what you can extract from document. You don't tell the computer what's the keywords, what's on the title. This is keywords extracted from text. Chrysler Space Dividend, optimism. Right. So actually, one of the students who did this work, actually he quit his PhD, or haven't yet. He just take a leave from his PhD. He's starting a startup company in China. So they already had a company are investing in this kind of techniques. And also protein. I think there's a lot of biomedical people. I'm by far not an expert, but there's someone my former student, Huang Kun, did to microarray data, gene versus protein, right? How to capture how gene regulate proteins, how protein influence each other, and there must be lots of correlations in the data, right? But the data could be contaminated. You want to find the truth, you better use a more advanced tool. This is my favorite example because for many years, if you play karaoke, you should like this. Because if you have a song, you like the music, but you don't like the lyrics, you want to remove it. So in the past, in the audio speech recognition people, they developed very, very sophisticated system to remove lyrics from the music. Turns out the solution is very simple. Do the short-time Fourier transform, do the RPCA, invert it back. That's it. Nothing else. And unless you write very, very bad lyrics, right? like da, whatever, that gets mixed with the music. But anything with some content will pop up as a sparse program. Because it doesn't have harmonics. Also, this is about internet traffic analysis. Or the algorithmic help you to detect anything out of the ordinary from day-to-day business, day-to-day traffic, right? Something happened. Or sometimes you have to manipulate the structure easily in the data. You have to manipulate the data a little bit to see the structure, to see the low-rank correlation, spatial time correlation. And of course, I come from a control background. I really have to say this because the whole business very much started from control people that try to identify dynamical system, and where you actually see the measurements, Hankel matrix, are naturally low rank. And in fact, the techniques of using nuclear norm to do low rank recovery was proposed by some of the control folks, Marion Fazel and Steve Boyd, very early on. And that has led to all the development, theoretical analysis and development. And anybody, there's a lot of people doing graphical learning, right? So you can infer some hidden graphs from some observables. Even for Gaussian network, probably the simplest class graphical model, Gaussian network, tree-like model. And if you want to infer the structure, infer the hidden nodes, you're actually solving a robust PCA problem. You probably didn't realize that. The problem is NP hard. Because you actually try to, because the observation, the inverse empirical covariance matrix is exactly sparse plus low rank. This is a line of work from the MIT folks, Wilski and Pablo Parello. You can see there's a wonderful paper in the Analog Statistics last year, follow up on this development. So, I mean, we see very, very beautiful parallel lines of stories, right? We cover sparse, low-rank structures from highly compressive, cropped measurements. And what do we say in mathematics, right? If you see an idea worked once, it's a trick. If it worked twice, it becomes a method. We really suggest something truly, truly universal and general. Well, actually, that's the case. Turns out that there's a huge family of structures called decomposable. Family of structure. They are low-dimensional structures in high-dimensional spaces. Sort of describing this kind of spatial continuity you're talking about. That has exactly the same phenomena. You can recover them using convex simulation from highly compressed measurements. You can add them together. You can separate them. You can add them together and project them, entangle them. You can always go back using convex simulation. You can sort everything out. Nothing is lost in your measurements. So as you can see, this is some of the latest development. The timeline is about last year or last couple of years. There's a huge family of strong theoretical results suggesting how advanced things you can do. But to be honest, many of the structures, we don't even know what they model in real data. So in that sense, the theory is way ahead of practice. Because the example you see today in my talk, there are few, still very intuitive. I still find them very banal, right? Because you can look at them and say that I got to have that. But what about certain things that's hidden, more deep, but can be described by more advanced structures in your signal, and we don't know. I have yet to be honest, I have yet to see such an example. Right? Really take some understanding of the structure to see a non-trivial matching of the model and the structure. I call it a perfect storm. Why? Because everybody talk about cloud, right? So if you have cloud, you have storm. And why it's perfect? It's the really beautiful mathematics, precise understanding what's going on. Wonderful. I mean, revolutionary ideas about optimization, how to scale up things, how to parallelize things. Really harnessing the kind of parallel distributed and the scalable computing framework we have. And also, data is everywhere today. And if you're successful, find one application, you can become rich. That's really one of the message why those areas really inject each other with lots of energy, lots of excitement. Again, the talk is not about one work. It's really about a slew of work that done with by me, students, and also lots of collaborators in this area. And if you're interested, actually, this is a website we collect actually not just our work, but also many papers or works, theory, algorithm, applications by others. This work just give a very small fraction of that development. So those are actually the real heroes, my former students, and also some of the colleagues at Stanford, and also this Emmanuel and Zhouchen, who developed the algorithm. Yasu has helped with many applications. So I have to really acknowledge them. They're contributions. Thanks a lot. Sorry, taking a little bit of time.
I'd like to thank Dr. Ma for a remarkably visionary talk, being both broad and unified at the same time. Rene had to go to his video, so he asked me to handle questions, but I'm sure you can put up your own hands.
So, I have a question about another technique which somehow relates to phase recognition. So, what is the kind of robust non-negative matrix factorization?
Yes, so in fact, keep in mind, robust research is also doing factorization. In fact, since you brought it up, I mean, there's actually a very kind of, in my opinion, a breakthrough by folks, actually my colleagues in India and also some folks, Jane, Peking, and all this, they actually be able to prove that the factorization method with in-country data provide a globally converging algorithm. Actually, using the proof ideas from robust research. So basically, even for matrix factorization, that people start providing theoretically guaranteed global optimal algorithm. Of course, in practice, you can always use whatever factorization method you think that you can incorporate more structure in your data. You may see some empirical gain. The point here is that how much data do you generalize? What can apply to other data? Or can you guarantee under what condition your method works? So that makes this line of work slightly unique in that sense that you have very, very complete theoretical algorithm and application related to each other.
I saw this paper I have read by Shapiro, who has done robust NMF with L1 constraints and things.
Yes,
I don't know, like, if you do robust PCA with an L1 relaxation and that. So what is the difference between, is there any major difference, a tangible difference that you see?
Not really. I think most of the work is mostly trying to develop for specific settings. I mean, the core of the techniques are similar. It's just that you have to deal with alignment, you have to deal with lightings, you have to deal with poses. So that's really that change the specific settings with a piece of it.
I'm curious, have you applied this technique to optical illusions? And what does it? So, for example, like MC Edgebeer is repeating cubes, right, where you can see it.
What is it? What's it done?
MC Edgebeer has the tessellated cube example, and you can perceive it either with the cube popping out of the page or popping into the page. So, does this system produce both solutions, or does it get stuck somewhere in the middle, right? Pulled equally by a gradient in both directions?
In this case, it will give you. Keep in mind, I think it will give both solutions, depending on how set up. Actually, I used that picture on the cover of my first book. Human be able to actually was able to perceive 3D basically from a single picture like that. Right. So certainly the techniques like this give you an answer to that. Maybe not a unique answer because both the mathematically are equally good answers here. Maybe just take one more questions.
I'll just ask a quick one. So once you've decomposed into A plus E, what happens if you run the technique again on E, perhaps finding some higher rank structure within E?
No, okay, that's a great question. So in fact, Marion Patel has recent work on that. Basically, that you discover structure that both simultaneously low rank and sparse. Turns out there's not much theoretical gain you can get out of it. In many cases you cannot. So, I mean, if you're for detail, I will refer you to her paper, Marion Patel of the University of Washington. She's the first lady proposing the nuclear norm for low rank recovery. At least one of the first. And so she has followed up. Basically, the matrix you try to recover is both simultaneously low rank plus sparse. How can you recover such a from noise or from corruptions?
So I'll follow up offline. Yes. Do we have any final questions before we break? Okay, let's thank Dr. Ma for